Everybody, I want to talk about simplifying complex fractions, which is just another name for dividing, basically, kind of. Anyway, let's get started. All right, so here's what a complex fraction is. Complex fraction is a rational expression that has rational expressions inside it, right? And you can take this to any number of levels. We could have, so here I've got this rational expression, right? It's a big fraction. But instead of having a polynomial over a polynomial, it's got a rational expression over a rational expression. So it looks like a giant mess. And I will say this, my students are often scared of this stuff. It's actually not very hard. Or it's rational expressions, so it's not, the easiest. But there are tricks to not being scared of it. So the first one that I want to mention is a thing that I've always been surprised, but my students really seem to like when I show them, which is this is really just division, right? Nothing has changed. This is just division. That's all fractions are. So if this first one, I can think of this as that. So it's really just 4 minus 6 over x divided by 2 over x minus 3 over x squared. And I've always found that when I write it like this, my students are less intimidated. So feel free to do that if it helps you. It doesn't make any difference to me if you want to think of it like this or like this. Same deal. When you're doing method 2, which we're going to learn about in a few minutes, obviously, it actually helps to leave it written like this. But it's totally fine if you want to think of it like that. That's all this is. So these are these, or I'm not going to do this example. I was going to say I'm going to do these examples and a couple other ones. Something like this, for instance, is barely even a rational or barely even a complex fraction. I mean, it is. It's a fraction over a fraction, right? But it's literally just this, just 10x squared over 3y divided by 4x over 6y squared, right? Which is exactly the same thing as 10x squared over 3y times 6y squared over 4x. Right, so hey, we simplified a complex fraction. It's really not that hard. So this is just division, right? Your big fraction bar is your division sign. So let's see how to do these. So the first one we're going to learn is what your book calls method 1, which seems like a fine name to me. And so method 1 is just you simplify within the numerator and denominator individually, and then at the end you put them together. You just divide at the end. So it's the thing that I was just doing. So what I'm going to do is I'm really going to simplify this and this separately. I'm just going to do them separately and then divide at the end. And that's method 1. I think method 1 is the most intuitively obvious, right? You do the pieces separately, then you put the pieces together, exactly like you'd think. So I'm going to do this on the next page. I don't think there's enough room here. So 1 over 4x minus 3 halves, 1 over 4x minus 3 over 2. I need to get a common denominator. A common denominator here is 4x, so I'm going to multiply this by 2x over 2x. And I get 1 minus 6x over 4x. And in the denominator there, I've got 3 minus 1 over 2x, and that's 3 over 1. So my common denominator is 2x, so multiply by 2x over 2x. And I end up with 6x minus 1 over 2x. And so this original expression is just 1 minus 6x over 4x divided by 6x minus 1. That's suspicious, over 2x, which is really just 1 minus 6x over 4x times, flip over the bottom, right, the thing you're dividing by, 2x over 6x minus 1. And I hope you're recognizing that 1 minus 6x and 6x minus 1 are negatives of each other, right? I can cancel those. It's the same things being subtracted, but in the other order. So when I cancel them, I just get left with a minus 1, minus 1. 2x and 4x obviously cancel. 2 cancels with the 4, leaving me at 2. X cancels with the x, leaving me with nothing, or 1, I guess. And the whole thing is negative a half. So it turns out that this, no matter what I put in for x, always comes out to be negative a half, which is really kind of funny if you think about it, right? It doesn't seem like that would be the case, but it is. And we can see that through algebra. So feel free to plug some numbers in here. Like I would plug in maybe a half for x, right? So that I would get 1 over 2 minus 3 over 2 is -1, and 1 over 3 minus 1 over 1 would be 2. So I've got -1 over 2, which is -1/2. Or you could put in 1,000 if you want, and just jam it into a calculator and see what you get, and it'll be -1/2. So kind of neat. But that's method 1. It's pretty straightforward. You take the numerator and you simplify it. You take the denominator, you simplify that, and then you divide them. Pretty straightforward. All right, let's see method 2. So method 2 is a little bit different. What we're going to do is I'm going to find what I'm calling here the big least common denominator, which is the least common denominator of all the fractions within the fraction. So in this case, all the denominators in the top or bottom, right? This is 4 over 1. So like all these denominators, I'm going to find the least common denominator for all of those. I'm going to multiply the top and bottom by that. So in this case, my LCD of 1x, x, and x squared. So my big LCD, I'll put it over here, LCD is x squared, because those things all go into x squared. So what I'm going to do is I'm going to multiply by x squared over x squared. And then what's going to happen is all the x's are going to cancel, or all the denominators are going to cancel, and we're basically going to get rid of 2 layers of fraction here. That's the idea anyway. So this comes out to be, so everything gets its own fresh copy of x squared. So we're going to have x squared times 4 minus x squared times 6 over x over x squared times 2 over x minus x squared times 3 over x squared. Let me block that off. And you might be saying, well, this looks worse, but I promise it gets better, because if you found this LCD right, everything's going to cancel, or all the denominators are going to cancel. So x squared times 4 is just 4x squared, 4x squared. X squared times 6 over x, well, this is x squared over 1, right? So one of the x's cancels, and I'm left with just 6x minus 6x. And the denominator here, one of my x's cancels, right? That's x squared over 1 again. I'm left with 2x. And here, the whole thing cancels, and I'm left with minus 3. Then we want to refactor. So when I take the GCF out of the top, I end up with 2x outside times 2x minus 3. And then my denominator is 2x minus 3. And the whole thing is just 2x. Now, it didn't simplify down to something this simple because we use method 2. It just so happened, like if we use method 1, we would get the same thing, obviously. Otherwise, they wouldn't both be valid methods. But yeah, so I tend to prefer method 2. I like the feeling of canceling out all my denominators and then simplifying something relatively easy. I think most students prefer this method, at least at first, until you get more used to it, and then method 2 is generally a little bit preferable. In all honesty, they're pretty much the same amount of work either way. Like nothing really changes difficulty-wise. So yeah, use whichever one you want. I'll never specify which one you have to use. They're both good. They both always work. Let's do another example here. So this was a slightly worse example. I'm going to do method 2 again. Yeah, I'm going to do method 2. So the denominators that I'm looking for is 1 over 1. I'm looking for this, 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 and this. And I didn't have it as my first screen this time, but factor everything. If you see stuff that can be factored, factor it. There's only one thing to factor here, w squared minus 9. And that's a difference of squares. That says x plus 3. That should be a w. Got the wrong variable there. W plus 3, w minus 3. There we go. So then I'm going to find my big LCD. I've got w plus 3, w minus 3, and w plus 3, w minus 3. So the LCD is just w plus 3, w minus 3. Now, here's how I usually write this. I'm going to write it like this. 1 over w plus 3 minus 1 over w minus 3 over 1 plus 9 over, that's a 9, not an A, w plus 3, w minus 3. And I'll leave it to you to decide if you want to write it this way. but I usually don't write a fresh copy of the thing I'm multiplying by in front of everything. I just sort of multiply in my head. So this goes to both this and this. Don't forget to do it to both of them individually. And when you cancel something, like we're going to do it here in a second, remember that each term gets its own fresh copy of the thing you're distributing. So 1 over w plus 3 cancels the w plus 3, and that leaves me with w minus 3 minus parentheses 1 over w minus 3 cancels with the w minus 3 and leaves me w plus 3 all over, well, we're going to get w plus 3 w minus 3 when I multiply by 1 plus 9 as the whole denominator cancels. Then when we simplify that, we're going to get, well, this minus sign gets distributed, so we're going to get minus w minus 3. We can get rid of the parentheses. There we go. Give my pencil back. W minus w is 0, minus 3 is minus 6. My denominator is w squared minus 9 plus 9. So we're going to get minus 6 over w squared. And I'm done. Yeah, there you go. That's how you do these. I want to show you one more thing. It's a thing that is on the homework and that you may see in the future, which is things of this form with specifically with h's in them. And you may have seen this before. It's called the difference quotient, which I'm not crazy about the name of, but that's what everybody calls it. And it comes from a thing in calculus. Believe it or not, this is a form of the slope formula. Like if you remember back when we were finding the equations of lines, this is the slope formula. I know it doesn't look like it. I'm not going to go into why it is the slope formula, but it is. And so you end up simplifying this sort of thing quite a lot. It turns out that calculus is actually very concerned with the slopes of lines, which might seem a little odd, but it is. It turns out to be super important in calculus. Consequently, this is a thing that you end up seeing a lot. So let's see how we can do it. Now, I think when you have something like this is probably going to be easiest if we use method 2 again. Yeah, I think so. So I'm going to have 3 plus 3h, 3 and 1 that I want to find the LCD of. LCD. So 3 plus 3h is, well, let me not do the LCD yet. 3 plus 3h is 3 times 1 plus h. So I'm going to have 3 times 1 plus h. So I'm going to have 3 things that I have in my, or I guess just 2 things that I have in my LCD. I've got 3 and 1 plus h. So that's my LCD. 3 times 1 plus h. And then I'm going to multiply the top and bottom by that. So we're going to have 1 over 3 times 1 plus h minus 1 over 3 all over h. I'm not going to write it as h over 1. You can if you want to, but I'm not going to. It's going to be 3 times 1 plus h over 3 times 1 plus h. And when I multiply, remember that this gets distributed to both things, and each of those 2 terms gets its own fresh copy. So when I multiply 3 times 1 plus h, it cancels with the 1 over 3 times 1 plus h, leaving me just a 1. And then the 3's cancel on the second one, and I just get 1 plus h. And don't forget the parentheses. And then the denominator is 3h times 1 plus h. I simplify the top, and I get 1 minus h. So I have minus h on top, and the denominator is 3h times 1 plus h. And when you're doing the difference quotient, when you're simplifying the difference quotient, it should always happen that the h in the denominator ends up canceling out. And this is for reasons that you will see much later in calculus if you get there. But expect that what you're doing will cancel this h out, specifically this h here, right? So I'm going to have this and this cancel. That's very normal. This ends up being minus 1 over 3 times 1 plus h. That's the whole thing. So there you go. That's all I really want to say about simplifying complex fractions. despite the name, the word complex right in there, complex just means inside itself, essentially, in this case. It doesn't mean hard or complicated. So there you go. That's simplifying complex fractions. I'm going to go ahead and stop there. All right, I'll see you guys in the next video.